You see that?
Okay. Yeah, perfect.
Okay. Right. I was just saying that I just wanted to show you this banyan tree, the Kirpak Medical College that I graduated from, and subsequent to which I went to SRMC for my MD. And I was just saying that this is where I am currently. I am the Deputy Director for Microbiology Services for Hunter, New England. So this is the map of New South Wales, and we serve a large area here in the northeast. And these are the number of hospitals we have. I have around 61 laboratories across the region. And this is where I am based, and in the northeastern state, the hospital called John Hunter Hospital, and with around 1,000 beds. And this is the research facility that I'm affiliated with. Okay, so as I was saying, I will start off with the family that the virus belongs to. I will try to keep it as simple as possible with structure and its implications. And I will talk a little bit about genomic composition and the implications in diagnostics, a little bit about pathogenesis in a very simple way, and also to understand how different it is to the SARS that we know about, which was an epidemic in 2003, as well as the MERS, and what, when, and how to test. But I am mindful about another talk that's coming, and I certainly don't want to step on her shoes. So I will keep to our experience here in Australia as to what we do and the things that work and that don't. Okay, so coming to the coronaviruses, I'm not going to show you the exact family tree because it can be a bit confusing, and I know that there are non-virologists in the crowd. So these are the common cold viruses. So if during winter, if you take a population with common cold or patients presenting with influenza-like illness, 1 in 3 will certainly, if you test, may have this coronaviruses. So the less pathogenic ones that live with us, that cause mild respiratory illness, which is no more than common cold, very unlikely to cause pneumonia. They can cause a bit of diarrhea sometimes, but they're usually not harmful. The other coronaviruses, which are the highly pathogenic ones, are the ones that we are concerned about, and we certainly have one now, which is the SARS, which we had in 2003, SARS-CoV-2, which is the second generation of viruses that we are concerned about now, and then the MERS-CoV, which is still present, but in a very confined region in the world. So the COVID-19 is the disease that is caused by the SARS-CoV. So coming to the structure, the coronaviruses have a very simple structure, right? So if you imagine a Ferrero Rocher chocolate, that's exactly what it looks like. So the name comes from the spikes or the crown-like structures that you see here. And this is the envelope of the virus. So the envelope covers the virus, and it covers the body of the virus that has got the nucleic acid, the ribosomal nucleic acid. First one being hosting the antigens on the surface and also in helping the binding. So the envelope is made of lipid particles, and therefore, as I said, lipid is prone to killing by alcohol, and which is why we encourage using alcohol and virus, in fact. But the plus side for the virus is that it can actually merge when spikes that you see, it merges with the human cell membrane and becomes almost invisible. Yep, becomes almost. I think there's someone who needs to mute. Yep. Okay, so I'll continue. So the envelope, when fuses into the human cell membrane, becomes invisible to the immune system, and that's one of the mechanisms by which it evades and gets into the host cell. Now, the structures apart from the envelope apart from the spikes, are the envelope proteins. The orange color dots that you see here, as well as the gray color dots, they're called as the membrane proteins. So the envelope protein as well as the membrane protein act as antigens, and they help to elicit immune response. Right? And inside the core of the virus is the RNA or the ribonucleic acid. And this is, in other words, the secret information code that the viruses carry. And this is what is ejected once the virus enters into the cell. And based on the information code, the human cell starts producing the virus particles, which are then let out to infect other human cells. Now, the RNA, for the microbiology students out there, the RNA virus is a positive sense virus, which means that the code that is present can be directly translated to proteins as soon as it enters into the cell. So there are some negative sense viruses, which means that the mRNA of the negative sense virus need to be translated to an active code before it can replicate and start producing other proteins. Another thing that you have to remember about the enveloped and the non-enveloped viruses is that the non-enveloped viruses are quite resistant to killing by alcohol, because obviously they don't have an envelope. They instead have a protein membrane. And we all know by chemistry, protein membrane is difficult to kill. You have to expose it to high temperatures for it to get denatured, or you have to use a bleach. Example would be a norovirus, which is why it causes a large number of outbreaks, although it is something that is not easily transmissible as such, human to human. It can stay in surfaces for a long period in time because of ineffective disinfection, and thereby causing a large outbreak. Okay, so coming to the genome, it's a very small genome, at least 100 times less than the human genome. And it's only 30. Okay, and apart from that, they also have other structural as well as non-structural proteins present. Okay, coming to a closer look, if you stretch the RNA genome into a single line, you will see that 70% of the genome codes for what is inside the virus, inside the core body of the virus, and the rest will code for the structure. Now, if you take the coronaviruses, the list of coronaviruses that we know, at least the 7 that we know, all those viruses have a similar genomic structure. They have the open reading frame followed by the several proteins that I showed you just now. But what is different among them is actually the amino acid compositions that you see in the spike protein, the envelope protein, the membrane, etc. And that helps us in a way to design assays specific for diagnosis. Say, for example, a specific RT-PCR to detect SARS-CoV, or a specific PCR to detect MERS, etc. Now, this is what we call as a phylogenetic tree, and people who have done sequencing may know what it means. So essentially, what we use is to understand the genetic structure or the genetic distance of a particular virus to the other in the family. And to some extent, we can also determine where it's evolving from. Now, the way to interpret this is to actually look for straight lines and the closeness between the viruses. So each line represents the virus that people have isolated and submitted sequences on. And if you see a single line like this one, these are all coming from the Wuhan, and they are all one single clone. So which means that they have a high similarity, and therefore it obviously is an outbreak. Now, then you go backwards and look at which is the next branch that is closer to this. And when you look at the one that's just below, which is coming from the batch CoV, and this is exactly what they were claiming as possible source for the Wuhan virus. So it is much closer to the Wuhan virus. The bat virus is much closer to the Wuhan virus than it is to the SARS-CoV, which we had in 2003. So you'll have to go another batch further. And then you have to go 3 more branches further to actually compare with the MERS-CoV as well as the human human coronavirus that we have as common cold virus in our population. So in other words, if you call the coronavirus as a child, then obviously the bat virus would be its sibling, the SARS-CoV perhaps first cousin, and the MERS-CoV will be the second distant cousin, a distant relative. That said, there are several similarities between SARS-CoV and SARS-CoV-2. Now, in terms of its pathogenesis, they both attach to what we call as the angiotensin converting enzyme receptor 2. They both have similar affinities, and these receptors are present both in humans as well as in bats. Now, remember that the bat is actually a swimming pool or a reservoir of several heterogeneous population of coronaviruses, right? So what we have seen is probably just 2 or 3 types. They are the reservoir, and they have the capability for some reason of ability to bind and multiply several heterogeneous population of coronaviruses. And it all depends on the susceptibility of a particular mammal to get exposed to the virus, and also the presence of a unique chemical structure of the binding receptor, which is the ACE2, that determines the host range. Say, for example, the SARS virus in 2003, we know that we had it from bats, but it went to the civets before it came to the humans. But then the SARS-CoV came straight to the humans. So it all depends on how strong the binding is going to be, or how the AC2 binds to that particular virus. Now, there's another similarity in terms of a protease enzyme that we wouldn't go further in, but it's interesting that they both carry similar properties with regard to the proteases. And as the previous speaker said, people have found that the convalescent sera from patients who had suffered SARS but actually neutralizing the SARS-CoV, but not to a greater extent. And that is probably because of the affinity that it exhibits, the similarity in affinity that it exhibits with the binding site, as well as in the spike protein. Okay, so as I said, just reinforcing the fact that both the SARS-CoV virus, the one that we had before, as well as the current virus, have similar binding affinities to ACE2 inhibitors, and that the neutralization sera that we obtain from SARS patients can to some extent prevent the entry. And this is the subject of research at this point in time. Okay, so once it binds to the ACE2 inhibitor, this slide may be a little bit busier, but I will try and go through and do justice to help understanding a little bit. So what it does is the SARS-CoV-2 virus binds to the receptor ACE2, which is the angiotensin converting enzyme inhibitor. As soon as it binds, the membrane fuses with the human cell membrane. The virus uses the human cell membrane as a shield to get into the virus, protect itself from the surrounding immunity. And once it enters into the cell, this is the time that you consider your human cell to have been completely hijacked. Now, what it does is, as soon as it gets in, it fuses, it releases the information code, which is the mRNA, and we know that it's a positive sense, so which means that it's ready to get replicated. So it sends the mRNA code and instructs the human cell to start producing the spare parts, and the spare parts are nothing but the spike proteins, your envelope proteins, and the membrane proteins that we just looked at, which is the structural and the non-structural proteins. And there is a different machinery that actually packs the spare parts together and packages it and then releases it out of the cell. And that then goes and infects the other cells. So this process occurs simultaneously, and therefore multiple cells get infected, and there's a very quick spread of infection. Now, this is a little bit in contradiction to, different to what we see with the MERS-CoV, because the MERS uses a totally different receptor to SARS-CoV. MERS sits and docks itself to a CD26 receptor, otherwise called as the DPP4. Now, this receptor is predominantly present in type 2 alveolar cells in the lower respiratory tract, as well as the kidneys, and which is why we saw a lot of patients with MERS-CoV to present with kidney failure or renal failure. Whereas the ACE2, the ACE2 inhibitors are present in multiple cells, including the type 2 alveolar cells, the vascular endothelial cells, as well as the kidneys. Now, again, people have studied closely the binding of SARS-CoV to the ACE2 inhibitors, and they found that not all the AC2 inhibitors can bind the SARS-CoV. It's only the apical, the well-differentiated cell, and also the AC2 inhibitor should be in the apical location rather than the posterior basal location. So there's a lot of factors for us that can actually help not getting infected, but the SARS-CoV is quite clever in circumventing those. Okay, so the other area where it's differing from SARS and MERS is in its epidemiology. So we have seen at least 10 times more cases with SARS-CoV-2 compared to SARS as well as MERS. And again, this could be either, due to the affinity of the receptor to the virus that probably is different, and also it could be something that, that's getting propagated via the asymptomatic transmission, which we haven't quite measured due to combination of factors and absence of immunity in the population. So this is just a comparison of the estimated as well as the cases that we have observed. But this is of 10th of Feb 2020, so not quite recent. But you can see that the case fatality rate in SARS is much lower than MERS, and in the SARS-CoV-2 it's much lower. And as previous speakers have alluded to, the recovery rate from SARS-CoV-2 is much higher and sits around 80 to 90%. Okay, a word about R0. I think the previous speaker mentioned about the R0 and what it means in terms of epidemiology. So R0 is nothing but a measure of how many people can get infected from one person. Now, this differs from disease to disease. It depends on the actual infection as to how it is spread, whether it's airborne or droplet transmission or fecal-oral transmission, and also depends on the existing immunity in the population. So for SARS-CoV-2, when it started, they estimated anywhere between 1.4 and 5.5. Now, the 5.5 is probably in a population which first encountered the virus, where there was no case finding, was very recent, probably in December or January, around that mark. And also the reproductive rate can go high in elderly and vulnerable population as well. But with control precautions and other social distancing, it's likely to reduce to 1.4. But the average is around 2.5 to 3. Now, one thing that you've got to remember is it's just not 2.5 and 3. It raises exponentially. So these two people can get infect another two, and then another 4 in turn, and so on. And within a short period of time, you're infecting a large amount of people in the community. And therefore, for every case that you detect by PCR or make a diagnosis of, remember that there's plenty of other undiagnosed cases in the community that would have already been exposed. Okay, so detection of virus in body fluids, as I said, we have very, very low detection of virus in blood as such, but virus is largely detected in respiratory secretions. And again, as the previous speaker alluded, this is a report from the joint WHO and China Commission in 2020 for the virus. And we saw that the asymptomatic transmission can occur at least 1 to 2 days before the onset of typical symptoms of a respiratory illness. And shedding can certainly extend up to 2 weeks in some severe cases. And remember that this is all by PCR. We don't know whether the detection of RNA translates to detection of live virus and therefore transmission. So it's all in early stages before we get more data on that. And it's also detected in 30% in feces, day 5 after symptom onset. And remembering the fact that the ACE2 inhibitors are also present in the GIT, and diarrhea for some reason seems to be a not the initial symptom, but somewhere in between. And the diarrhea can persist for quite some time. And the viral shedding in feces, they claim, can go up to 4 to 5 weeks in moderate cases. But the question that we don't know or we don't know the answer for are whether the extended detection translates to true viral shedding, as we said, particularly in feces, and whether that contributes to a certain level of herd immunity. I guess it's too early to decide that. And also, what is the role of fecal-oral transmission in such a scenario? Okay, so this is a study that looked at serial sequential sampling on patients, multiple sampling from patients serially throughout the illness. They didn't have very large amount of data. It's very, I think, limited 20, 25 patients that they did the study on. But what they wanted to study is to see which specimen offers the best sensitivity, whether it's the lower or the upper respiratory specimen. Now, this is quite critical for us to understand because at the start of an epidemic, you want to get the most out of the specimens that you collect. In other words, you want to have a test that has got a better sensitivity and that is boosted by the type of specimen that you obtain. And therefore, the study concluded that the bronchoalveolar lavage, which is of no surprise, just because the type 2 alveolar epithelial cells harboring more ACE2 inhibitors is the best virus that you need to kill 50% of your cell culture. In other words, this is a true live virus that you need to kill, that needs to kill 50% of the cell culture. So this is the accurate reflection of what we would see in real time. So they compared the HCoV, which is a new coronavirus, with the previous SARS virus, and they determined that in aerosols they can stay up to 3 hours, right, live. And in copper, which is probably why our grandparents were cooking in copper vessels, it declines and doesn't stay alive for more than 4 hours. And with cardboard, it probably does not find it impressive or attractive, so it declines to 1 hour. It doesn't stay any more than 1 hour. So if you get a consignment, perhaps just clean it on the outside, and then as you remove layer by layer, just keep cleaning, keep your hands clean, and that should protect you from any viruses. And on the steel surfaces, which is a bit disappointing, it can thrive up to 24 hours. And which is why we have to be a little bit careful about using the forks in the restaurants and so on. Remember that it can stay for a longer period of time, and same with plastics. Okay, this is going to be my last slide, I think. So with specimen testing criteria, this is certainly our experience. We have 3 groups of patients that we have stratified. One group is the ICU/inpatients. The other group is suspect healthcare workers, because we would like to consolidate and protect our workforce, and we want them to return as soon as possible, and also try and prevent the spread in hospitals. So we have them as a separate criteria. And then the third criteria, what we call is fever clinic. So you may have heard that in many countries, just because of the load, the burden of the patients who may be presenting to hospitals, like what Dr. Jayanti mentioned before, we do have some fever clinics in select locations, and where the well patients can present themselves if they satisfy the epidemiological criteria and they present with fever and some mild respiratory symptom, not really serious enough to warrant an admission. We have different testing pathway for these 3 groups, which I'm quite happy to share after the meeting. But for time constraint purposes, so I'll just say that in order of preference, bronchoalveolar lavage when you have a patient in ICU, sputum, nasopharyngeal swabs, and nasal swabs. Now, a word about nasopharyngeal versus nasal. It's quite hard to obtain a nasopharyngeal swab, so I think we all understand that. It induces a cough, and therefore I would suggest having some airborne precautions, or at least having your PPE before we try and do that. The nasal swabs is pretty straightforward. I don't have any strong evidence to say that nasal swab is inferior to nasopharyngeal. But if you can obtain a nasopharyngeal swab, it is much better, because of limited experience that we have had with our PCR positive. The CT values tend to be a little bit lower for nasopharyngeal swabs compared to nasal swabs. And we also collect serum for storage, and this is purely for research, as the previous speaker mentioned. So we collect serum from ICU and ward patients just because we can collect from these people. We don't bother collecting from fever clinics people, because obviously the strategy there is to get rid of people as soon as possible from the hospital so that they don't infect others. And we do certainly collect serum from healthcare workers, because we would like to know at a later point in time as to whether they have had an asymptomatic exposure. So the tests that we perform include the SARS-CoV specific PCR, which is a real-time PCR looking for the different genes. Now, WHO protocol says we need at least 2 genes before we call it positive, but this is what we have been doing. But with a shortage of primers and probes, we have restricted ourselves to just 1 gene, and that gene would be the RDRP, because it shows a sufficient difference or a genetic dissimilarity between the SARS-CoV as well as the SARS and the MERS viruses. Obviously, you want to maintain specificity for your reaction. And of course, we perform viral culture, but only in referral laboratories, again for vaccine studies and some neutralization studies. We don't do it regularly. And of course, as I said, we do serology now that's available in some Australian laboratories. We look for IgA, IgM, and IgG. And I have provided a link there that actually gives you much more information about the PCR and the different protocols that one can adopt. And I think, to conclude, I think we are going back to our Indian roots, and what works best is saying vanakkam and social distancing and wear your PPE, because the Queen seems to be following that pretty pedantically. I think she wears gloves all the time, and of course, eat with your hands. That's the best. And thank you, and happy to answer questions.
Thank you, ma'am. Before we go to some of the questions which have come in, I have a kind of an announcement to make. This is even a request. This is an academic forum. I suppose all of us understand this. And at this point of time, the concern of the medical fraternity the world over and all those agencies which are working with the health sector, including the WHO, the focus is on containment of viral transmission and fighting the onslaught that has been caused by COVID-19. So at this point, we are not entertaining questions or comments or opinions which could probably hurt the sentiments of specific communities, specific groups, specific countries. Let me make it very clear. We are not entertaining questions and comments which probably could affect the sentiments of a group or a community or even a single individual. So that is a responsibility that all of us owe to the society. So let's stick to that dignity. And ma'am, as you rightly said, Vanakkam and Namaste may be the call of the day. There are a few questions here. How long does the virus stay or survive in clothing? In clothing, how long does the virus survive? Ma'am, can some insight on that?
Yep. I think I'm being muted. Yeah. Can you hear me now?
Yes, ma'am, yes.
Yep. Okay. So I should be honest with you. I don't know the answer to that question. So what we know is that it can stay longer in some surfaces, as we have seen in some of the studies. But I don't think I have a number for the length of stay of the virus, the survival of the virus in the clothes.
Thank you, ma'am. And there's one other kind of, tone question to that. Can we suggest salt water gargling? What is your take on that?
Look, I don't know the science behind it, but I tend to believe what my parents said to me. So I certainly practice, and I certainly ask my children to do that when they have a scratchy. I'm sorry, but I think there should be something, and I have definitely found some relief for scratchy throats. I'm not saying that that's a treatment. I'm not a person specializing in alternative medicine or anything. Just what my parents have told me, and I think that seems to work.
Thank you, ma'am. And Government Medical College, Karur. Karur, are you in? Government Medical College, Karur. Karur, Madam Rosie Vanilla, we can see you. You're in, ma'am. You have some comments. Madam Rosie Vanilla, herself a microbiologist. Ma'am, some inputs from you.
Very good morning, madam. I just joined this webinar a few minutes ago, and it's been very clear. Are you able to hear me, madam, on the other side?
Yes, ma'am, you're very clear. We can see you clearly. We can hear you clearly. Please go on, ma'am.
Thank you very much. Now, thank you. It was a very wonderful listening to the testing strategies, etc. But regarding saltwater gargling, we usually used to encourage it in terms of increasing the salinity around the throat and discouraging bacterial growth. But regarding viruses, I have no idea.
Ma'am, sorry to interrupt you. Can we request your audio person to slightly reduce your volume, especially, and I think the phone, probably reduce, whichever gadget you're using, the volume will have to be reduced. There is a lot of resonance and there's a lot of echo here.
Is it okay? Is it okay now?
Yeah, that's okay. Probably everyone has their phones switched on or something. Can we kind of reduce the electronic interference? Yeah, please go ahead, ma'am.
Yes, madam. I think they.
Go on, ma'am. Please go on.
Yeah. Now am I audible, madam? Is it no?
Madam, the moment you said things right, I would like to ask a question from one of the IMA group. Dr. Hemlata, we have been talking about the antibody titers, and you did mention about the PCR status as they are in the incubation phase and in the presentation phase, and people who die up. There is a question from the floor. If and if you need to monitor a quarantine patient declared treated out, there is a
Okay.
definitely
So,
cause of concern that they still continue to be infectious. So is there any way, like checking their antibody titers, say above which antibodies have come, they stop shedding the virus? Is there any research which is focused on these lines so that we have a clear-cut laboratory evidence to declare this patient safe to be left into the society after the completion of quarantine?
yeah. So I don't think we have any firm evidence on that, but what I can share what we have here as a protocol. So for people who we home isolate, we go by the 14-day strategy. We test them every week, once a week, and at the end of 2 weeks, we give them 2 swabs to test, and they have to have 2 negatives before they go into the population, or say, for example, a healthcare worker who is positive, and for them to resume work, we need at least 2 negatives. Now, I don't have a firm evidence for this. This is all based on the data that's coming out of PCR and the test results that we have had from other labs.
Thank you.
And we do have patients sometimes who clear within a week, and we sometimes have patients going on for 2 to 3 weeks.
So at this point of time, the data is nascent enough to make a
RNAs. So during our transport and using the Dacron swab, are the RNAs discouraged? Is it the safe way of transporting? Because we don't want the RNA of the virus to be destroyed by the enzyme. So
Yeah.
is that the samples and the medium, are they okay for this?
Yep. So what we have seen is this is all the data coming from the flu studies. The dry swab without a wet medium is not as good because the virus for some reason doesn't elute that well in the medium. So we would, I'm not quite sure about the availability of the swabs. Here is what we call as a, and it automatically comes with 2 swabs in it. And I certainly wouldn't recommend the same because it's in shortage again. And we have now started doing the single swab with medium. If you don't have that, my suggestion would be to get the dry swab, and you can swirl it in saline or Hank solution in your laboratory, and that way you will be able to elute it well. And we have certainly seen sensitivity go higher.
Yeah,
Here we
thank you,
use
ma'am.
the
Thank
viral
you.
transport medium. Himalaya, we're using the viral transport medium, and I think it is wet. It is a wet swab because
No, that should work.
viral
Yeah,
transport. It should be okay, isn't it?
Yeah, that should work because we have now put contingencies in place, and there's a shortage of supply of swabs in Australia as well as the reagents for the testing. So we don't have reagents for any more than 2,000 tests at the moment. So we are trying hard to prioritize. We want to be very judicious in sampling patients, and we sometimes turn patients back saying that they don't deserve to be tested, or it's better that they isolate rather than to get